We have started chapter number 15, which is the kinetics of particle by using impulse and momentum. So we discussed about the principle of impulse and momentum, and we also solved some problem related to it. We also started a topic which is called as impact, and in that topic we also have studied the central impact. Now it's time you to learn about the oblique impact. We know that impact occur when two bodies collide with each other. So when they collide with each other, the line passing through the center of their mass is line of impact, and the line which is perpendicular to that plane or the line of impact is called the plane of contact. So over here we have an oblique impact in which uh, we have the component of the velocities along the line of impact. So this is the case in which we have two balls A and B, and they are colliding with each other, and they are having, and their velocities have some angles theta 1 and phi 1 before the collision, and after the collision it will become theta 2 and phi 2. So in order to understand this problem, let's see over here that, for suppose we have this ball A, and it has some uh, momentum along the x and y axis, right? So what we have done, we just resolve this velocity into its component. So this is its va1x, and this is, sorry, this is y, and this is x. So we have just we have written this velocity into its component. This is vax1 and this is vay1, right? And after some time the impulse is uh, the impulse the body B strike on it, creating some impulse on it, and after that it has moved its velocity. So after that we have this ball A, and after that it will move with some velocity va2. So similarly we have resolved this velocity in components. So we have one component along the x-axis and the other one along the y, right? So we have written this into this form, that after the collision with the body B, its uh, velocity change, and now it will become mavay2 and mavax2, and similar is the case with the body B. So when these bodies have collided with each other, we can apply the conservation of momentum along the line of impact. So we have this equation, which is mv1 plus mbv1. This is the initial momentum and this is the final momentum. Similarly, we have applied the coefficient of restitution equation, which is the ratio between the final and the initial velocities. So this is the equation for the line of impact, and we have also applied the equation in the plane of the contact, which is the perpendicular line, to the line of impact, and in which we have you can see that these velocities remain as it is. So we have an oblique impact in which bodies are not colliding head on. So you can see that the only component of the velocities which take part in this collision is along the x-axis, or the component of the velocity which act along the line of impact. Similarly, those components which are parallel or the perpendicular to the line of impact uh, does not play its part, and it will remain unchanged. Similarly, you can see that this is the initial momentum of the body or the ball A, and this is the final momentum of the ball A, which remains unchanged or remains conserved. Similarly, this is the component of the velocity, and this is the momentum of the ball B, and this is also the momentum of the ball B. So it will remain constant. So the only component which take parts due to the collision in the collision is the uh, component which is along the line of impact. So this is the complicated case in which you have to calculate the final velocities or the magnitude of the final velocities, and similarly the direction. So in this way you have four unknown. One is the velocity 1 and 2, velocity of A, velocity of B, similarly the angle of the velocity and angle of the velocity B. So in oblique impact we have to find the four unknowns. So let's see that when we have a problem related to oblique impact, what is the procedure to solve it. So this is the procedure for the analysis of the central and oblique impact, in which we have to first define our plane of contact and the line of impact. And you know that when we have an oblique impact, then we can apply the conservation of momentum and the coefficient of restitution equation along the line of impact. Similarly, uh, we cannot apply the uh, coefficient of restitution equation along the plane of contact, because the component of the velocities do not take part in the collision. So we can only apply the conservation of momentum equation along the line of impact in the oblique impact. So now let's solve some problems so that we have a clear idea that how we can analyze the central and oblique impact. Now we are going to solve some problem related to central and oblique impact, and in order to solve these problems we have to first identify our line of impact and the plane of contact. Then we will distinguish that whether the impact is either central or the direct impact. So if our impact is central impact, then we will solve accordingly. Otherwise, if it is oblique impact problem, then we will solve with the procedure which we have studied earlier. Now this is problem 15-64, and in this problem you can see that we have two balls. One is moving with the velocity 8 meter per second and other one is the 4 meter per second. This ball A having a mass 3 kg and this ball having a mass 2 kg, right? Then the coefficient of restitution is given, which is 0.7, and we have to determine the velocity of each ball after the collision. So you can imagine that when these two balls collide with each other, then if this is their mass center, then this will be the line of impact, and this will be the plane of the contact, right? So as we can see over here that we have the velocities along the line of impact, so that is why we can say that this is a central impact, and we will solve the problem with the procedure regarding the central impact. So let's move ahead and solve this problem. So this is 3 kg, this is 2 kg, right? So we can apply the conservation of momentum and the coefficient of restitution along the line of impact. So So over here the momentum before and after the collision will remain conserved. So we have mass of ball A and the velocity of ball A plus the mass of ball B and the velocity of uh, ball B. This will equals to the mass of ball A, the final velocity of ball A, right? Plus the mass of ball B, velocity of ball B. So over here, this is 3 and we have the initial velocity which is 8, right? So this is the direction, this is our positive direction. So this will be plus 2 and we have minus 4. Similarly, we have 3 and this is VA2, right? And plus this is 2 and this is VB2. So this is our equation 1, right? Now we will apply the coefficient of restitution equation, which is E it equals to this is our positive direction. So this is VB2 minus VA2 divided by VA1 minus VB1, right? This is our formula. So when we'll apply on this problem, then we will get the final velocity as VB2 minus VA2. These two final velocities are known, right? Divided by the initial velocity. So in this case, we have 4, which is with the minus sign. Uh, so this is uh, so this is 8 minus minus 4. So when you will solve it, you will get uh, this is E, which is 0.7. So we have 0.7 multiplied by 12 is equals to VB2 minus VA2. So this will be our equation 2. When you solve these two equations simultaneously, you will get velocity of VB2 will be 8.24 and meter per second. Similarly, you will get VA2 is equals to minus 0.16 meter per second. So that is how you can solve the problem or a central impact problem by using this procedure, in which you can see that uh, the final velocities are 8.24 and minus 1.16, and minus sign indicate that it is moving in the left side. So that is how you can solve such problems. Now let us solve another problem, which is problem 15-93, and in this problem you are provided with two discs, disc A and disc B, having the mass of 15 kg, and this is for A, this is 15 kg, right? And the mass of the disc B is 10 kg, so this is 10 kg, right? And when they collide with each other, we have to determine their velocities after the impact, and the coefficient of restitution is given, which is 0.8. So over here, when they collide with each other, we will join their center of mass, and this is the line passing through their center of mass, and this will called as line of impact. Similarly, we have a line perpendicular to this line, and we call this line as plane of contact, right? So in this problem, we have identified the line of impact and the plane of contact, and over here we can see that we have a component of the velocity along the line of impact and the plane of contact as well. That is why we can distinguish this problem as, or we can say that this is the problem related to oblique impact. Now in order to solve this problem, first we have to resolve our velocity along the line of impact and the plane of contact. Then we will apply the conservation of momentum and the coefficient of restitution along the line of impact, and then finally we apply the conservation of momentum of the disk A and disk B separately along the plane of contact. So let's solve this problem. In order to resolve this velocity, let me draw the axis. So for the direction, this small triangle is given. So for suppose this is the y and the x-axis. Similarly, this is the line. This is the line of impact, which is making an angle 53.1. How can you get 53? By taking tangent inverse of 4 divided by 3, and you will get this theta, right? So this is 53 angle. Now let me draw that 10 meter per second velocity. So if I just extend this line, in order to resolve that line, this is my 10 meter per second, right? When I resolve it, I will get this in the downward direction and the upward direction. So if this is 53, this is also 53. So this is also 53, right? So this is my component, which is the line of impact, and this is the plane of contact. So this is the component of the velocity along the plane of contact, and this is the component of the velocity along the line of impact. So this is the cos 1053. So you will get this velocity along the line of impact. Similarly, if I want to resolve this velocity, which is 8 meter per second, then I can extend it. I can extend it in this way, and see, this is its component along the line of impact, and this is the component along the plane of contact, and you have this angle which is 53.1. So this is the velocity, which is 8 meter per second, and this is 10 meter per second. That is how I have resolved these velocity. Now in the next slide, we will directly use the component of the velocities and will further proceed our solution. Now along the line of impact, we can apply the conservation of momentum equation and coefficient of restitution equation. So we have this is sorry this is our positive direction. So I can apply the conservation of momentum equation. So mass of ball A plus the velocity, which is VA1 cos theta, plus the mass of body B, here disk B, and this is VB1 cos theta, which is equals to the mass of disk A to the VA2 cos phi 2, and we don't know this velocity and this angle. Similarly, this is mass of this B to the VB2 cos phi B, right? So these are uh, the angles after the impact of the velocities. Now we will put the values. So we have the mass of the disk A, which is 15 kg, and over here you can see that it is positive. So the velocity is 10. We have cos 53.1. Similarly, we have the mass of the disk B, which is 10, and this is the negative direction because it is moving in upward direction, so that is why it should be negative. And we have the velocity, which is 8, and this is cos 53.1, right? And it will equal to MA VA2 cos phi 2 plus this term. So this is our equation 1. Right now we will apply the coefficient of restitution equation. So it will also positive in this direction. So E is equals to, this is VB2 minus VA2 divided by VA1 minus VB1, right? So this is our formula. When we will apply this formula to this problem, we will get the VB2 cos phi B. Similarly, so this is A, and minus VA2 cos phi B divided by, we have the velocity of A, which is 8 cos 53.1 minus, and we have this upward direction minus, and it will be 10 cos 53.1, right? So this will be your equation 2, and the value of E is given, and which is 0.8, right? So up till these two steps, this is the these are similar steps as we have solved in the previous problem. So simultaneously you can solve these two equations to get the final velocities in terms of cos phi b and phi a. Now let's apply the conservation of momentum of the disk A and B along the plane of contact to get the sign component of the velocity. Now along this is our plane of contact, and we have discussed that the components of the velocity along the line of impact will participate during the collision, whereas the component of the velocity along the plane of contact will remain as it is. So that is why for body A or the disk A, we will have the same component, it will remain as it is. That is why we have the momentum of A will conserve along the plane of contact. That is why this is the mass of A, the velocity of A sine theta. Sorry, this is sine theta. right? This will be equals to the velocity or the momentum after the collision. So this will be ma v, this is va1, this is va2, and this is sine phi a, right? So this will cancel with each other and you will left with va2 sine phi a, and this is equals to the 10 sine 53.1, and you will get 8, right, meter per second. Similarly for body, for this b, uh, the momentum of body b is mb va vv1 sine theta is equals to mb vv2 sine phi b, right? So you will get the velocity after the impact in terms of the sine component. So you will get vb2 sine phi 2 sine phi b is 8 sine 53.1, and we will get 6.4. So in this way you will have the four equations, and by you have the cos component of the velocity after the impact in the previous equation. So if you want to calculate this phi a or phi b, you can simply apply the tangent phi to the sine phi a to the this is va2 sine phi a and va2 cos phi a, right? Similarly, you can find the phi b. So when you solve all these equations, uh, you will get va2 has 8.1 meter per second. You will get vb2 has 9.3. Similarly, you can get phi a 102 degrees and phi b 43 degrees, right? So that this is the procedure for solving the problems related to oblique impact.